Next, so we have AJ Purdy here to give us a talk. Okay, AJ Purdy is a research scientist. I will just let everyone know you better. I'm sorry for put you on spot, but this is what I get. And he's also a adjunct faculty in the Department of Applied Environmental Science at CSU Monterey Bay and NASA Ames. He's a science team member of OpenET, serves as a technical expert on evapotranspiration for NASA Western Water Applications Office. So he is definitely a very important role in our OpenET team. I will hand this stage to AJ.
Thank you. Thank you. It's great to be here. It's nice to share on a project that I've been working on for about a year now, related to exploring how we might be able to harness evapotranspiration data as it relates to wildfire risk. And so this project, while Anderson's work was kind of focused on South America, and a lot of the work that we saw yesterday was really in national coverage, this is kind of zooming into my backyard in Central California. And so bear with me as we go through this, and just want to acknowledge some of the other co-authors here listed below. And so growing up in California, the things that mattered, it's like water availability and, and more recently, fires and fire impacts. And so that's kind of where I'm in the fortunate position to have kind of gone down the path of studying evapotranspiration and now trying to apply that to better understand how we might be able to mitigate some of the growing threats of wildfire. When you look at just the burned area across a lot of the states in the western United States, you're seeing on average we're actually accumulating more burned area on the order of about 75,000 acres per year. And this increase in burned area doesn't come without costs. For CAL FIRE, which is one of the wildland firefighting agencies in California, I think it's like 2020 here, they had cost exceeding $1 billion for fire suppression. And so, while this kind of like sets the stage, states like California have been really thinking hard about how we can more proactively, mitigate against these risks. And that comes between manage fire and forest and fuels thinning. Yesterday, and I think a lot of the research related to evapotranspiration and fire is really focused on the impacts of fire on the water cycle and how things like proactive management and fuels reduction can actually increase water yields for some places. And while I want to underscore the extreme importance of this type of work, what I'll be focusing on is really, it's like, what is that information we might be able to harness leading into those fire events? And just for context here, this is a fire that occurred on the central coast of California down in the Big Sur area in 2020. And so you can kind of see the average ET in inches leading into that fire event in 2020, about August, and how that impacts not only reduces ET the following year, but you might be able to use this information to track hydrologic recovery. And so as I mentioned, it's really, the question is, like, how can we use ET data to inform fire risk and support more proactive management? And so that kind of means focusing on that signal leading into these fire events as one way to explore this topic. And the interesting thing when I started kind of diving into this project was, let's kind of see what the drivers of wildfire are. And so what you're seeing on the right here, if you're unfamiliar with fires, is really the wildfire behavior triangle, as many people kind of call it. It kind of has three corners, one of which is topography, so kind of steep slopes, higher elevations. Those can kind of increase winds and really kind of promote more rapid fire growth. The top, we have weather, drier airs, hotter temperatures, both of which, dry out the landscape. And down in the bottom left, we have fuels, not just the amount of fuels, but the state of the fuels themselves. And so when you kind of overlay, all those inputs to ET modeling onto this wildfire behavior triangle, you kind of see that there's a really natural and organic overlap. In particular, required inputs for ET modeling, net radiation, temperature, and humidity, they all contribute to the fire weather indices that you may be familiar with if you live in one of these fire-impacted regions. Vegetation indices are able to kind of account for vegetation abundance and health. And as Yun kind of shared yesterday, the importance of LST to better actually identify periods of stress. In addition to that, the ET data itself is directly mapped onto the fuels. When we have higher evapotranspiration rates, especially in forested systems, where a higher fraction of that total ET goes to transpiration, those higher rates are going to be more indicative of higher fuel moisture states in those systems. And so, taking advantage of all of this, you may be saying like, hey, AJ, this is great. ET is the perfect solution to go and kind of deliver fire risk information by itself. But in conversations with some of the local agencies, and particularly the local CAL FIRE unit, ET data is just not part of their vocabulary yet. And that's because they really focus on something called live fuel moisture content currently to better understand the fuel state of their environment. This is really used by the agencies, in California and other parts of the country to evaluate and assess fire risk. Live fuel moisture in its simplest sense is just the ratio of water to dry mass of plants. And it's really affecting the rate and intensity at which fires can burn. And when you combine that with the dead fuel moisture, like the litter fuel moisture on the ground, it also provides a key indicator of kind of ignition probability if you have dry lightning events. And there's been some great research recently kind of indicating that. And so this top figure on the right just kind of shows you, how different levels of fuel moisture might impact fire behavior. And the one thing I'll kind of point out down here is that, prior work has kind of used on-ground observations to look at, when fuel moisture kind of dries to a certain point, do we see like an inflection point for fire growth? And this study down in Southern California kind of identified that point around 80%. But as you can see in this table in the top right, it's like once you get below 100%, that's when fire activity is kind of heightened. And when you drop below 80%, it's even, can be more extreme. And this plot in the bottom left here just kind of shows you one of the ways in which the local CAL FIRE unit that covers Monterey and San Benito County in Central California looks at fuel moisture. They're looking at the seasonality, and it's like how the station's data may compare to previous years, but then also how it compares to these previously identified key thresholds. Unfortunately, these data just aren't available, right? Like ET data was an enormous gap before, fuel moisture data are limited. Sampling is time intensive. It requires kind of going out to a plant, clipping branches, taking it, putting it in a tin, going back to the lab, weighing like the wet and the dry difference as a way to get the fuel moisture state. In addition to accessibility, these are going to be opportunistic samples. While I love to go hiking in the back, country, you're not going to go hiking in 6 hours like up a hill to get one sample to kind of benchmark it. It's just unrealistic and not practical. And in addition to that, if you kind of like look at that distribution, the frequency at which we're collecting and sharing these samples is unevenly distributed. At best, during peak fire season, there's about 100 samples in California alone. And again, kind of like in our backyard in Monterey, there's really only 5 pieces of information to consider a county-wide evaluation of fire risk. And so, this is where it's, obviously I'm kind of leading into, the value of using satellite-based information to kind of fill in these gaps. And before I kind of present, what I've been working on, I just want to acknowledge a lot of the prior teams that have contributed to this area. A lot of the early ideas for this concept really came out of groups in Australia, specifically led by Marta Yebra's group. But in addition to that, more recently, there's been some really awesome work coming out of Stanford and Alex Koning's group there. But while these approaches have kind of shown support for this approach to kind of fill in these gaps, I would argue that there's still some opportunities to improve this. Specifically, some of these models are kind of really tied to, if you get into like the nitty-gritty details of remote sensing, it's like machine learning models kind of tied to specific radiances or backscatters. They're going to be limited to the lifetime of those instruments. And so by kind of like harnessing modeling systems instead, we might be able to extend that record back in time and provide an operational source moving forward. In addition to that, improving the spatial and temporal resolution and building on a lot of the great work in the larger OpenET group in terms of lowering the barriers of access to data, I think is going to be key. And so what I've really done is kind of, leverage that overlap between, ET data and the wildfire behavior risk, and used a machine learning model framework at this point in time to take advantage of all those samples that have been collected over time in California. And so you can see, after you kind of do some quality assurance for, the OpenET record, we have around 9,000 samples in California to train on. And the figure on the right is just kind of showing the data that was withheld from this training process. And the takeaway here that I just want to share is that, while this is kind of like an initial, model that I think we can kind of continue to learn from and build on, it's showing accuracy statistics that match up quite well to the prior approaches at coarser spatial resolutions. And one of the things that I kind of took from some of the other prior implementations of, satellite-based live field moisture is really this kind of like looking at the change in some of these variables leading into a point in time. So not just looking at today's ET, not just looking at today's precipitation, but looking back 30 days, looking back 15 days as a way to kind of understand how those hydrologic variables are changing leading into a given day. Excuse me. And with that, this is what we get to start working towards. It's really like wall-to-wall coverage of live field moisture content at scales that are relevant for management. And so, based on this work so far, I've been able to kind of get to the point where I'm able to get down to a daily map of live field moisture content. But in order to kind of allow for the adoption of this data by agencies, I think one of the things that's been resonating here at this conference this week is really building trust in the data. And so simultaneous to the effort of developing machine learning part, I've been fortunate to work with a number of students in actually collecting on-ground samples to help build that trust in our backyard. And so this black area here that you see near Carmel, California, is really where I'm going to zoom into here. And we really had two goals. Are we actually capturing the seasonal drying? Are we capturing the spatial patterns? So this is just kind of zoom in to kind of showcase the difference of field moisture across these landscapes. And so just as a first kind of step, I was fortunate to work with some of the local agencies that manage land, the Monterey Peninsula Regional Parks District and the Santa Lucia Conservancy, which manages a huge preserve in the region. And in terms of access, working the preserve was awesome. It happens to be a place where there's a bunch of super rich people that bought into this neighborhood that have huge easements on their property. And so they were fortunate enough to allow us to come and collect samples in the areas that are preserved on the property. It just meant, being able to cover a decent transect. And when you look at, how live field moisture may vary from different locations on this map, in the top left, we're trying to kind of strategically sample things like north-facing aspects. In the bottom left, more of a south-facing aspect that includes a mix of like chaparral and oak woodland, which is very common across this area. And in the top right, for instance, you can see that we do have room to improve. And so, this just happens to be like a ridge top where we have very dry vegetation like chamise and manzanita. And, one of the things that we learned, this is, just based on like data collection from the last year, is that, there's a lot of variation across different species of what we're collecting on the ground. When you look at things like coyote brush, and, you can see that it sustains higher moisture levels like across the fire season, while some of the key indicator species that are commonly used, such as chamise and manzanita, have much lower moisture contents. And, along the way, it's like through discussions with, the environmental scientists at CAL FIRE, they helped us identify which species we might want to consider targeting as a way to help them better understand what the composition is of, fuel moisture across the landscape. And so, just for reference, it's about a range in about, 40% or so for fuel moisture. But in addition to that, wearing one of the NASA hats, they kind of learned that I was doing this work in Carmel Valley, and NASA has a new program called FireSense, and I'm fortunate to be part of that very minor role, part of the implementation team on the pre-fire focus group. And so, they were flying airplanes across the western United States. they're trying to capture pre-active and post-fire conditions. And so when they reached out, I was like, yeah, absolutely, I'd love to kind of, participate. And one of the things I want to highlight, which is a really great experience, you can see the airplane in the top right here. I was expecting more of like an Indiana Jones moment, having airplanes flying over. It was much more anticlimactic. But, the thing here to highlight is that I had 9 students come and participate in this work. And so it's not just 9 students participated, 9 students showed up on a Wednesday morning in a parking lot at 6 a.m. to get out to the field station on time. And so, just as, sharing their participation, this is Ronnie and Marie. They're 2 students that contribute to our lab. And so you can see we really targeted intense sampling in 4 locations across, a site closer to the Carmel River, which is more of a riparian corridor, more of that oak woodland, and then more of like the chamise drying area. And when we compare that to the fuel moisture model, the takeaway here is that, while we see a lot of variance, like in terms of samples that were collected on the ground, when you take the average of each one of those 4 locations, we're actually capturing these differences at a fairly reasonable degree of accuracy. And so again, I think, we have some opportunities to learn and improve this model, but at this point in time, I think it's showing support in order to provide, at best, like usable data in the near term to explore opportunities. And this means like delivering data in accessible formats. It's like one of the things that we've identified with the local unit that we want to explore is how this data might be able to be integrated into their planning for prescribed burn activities outside of, a traditional fire season. For instance, like trying to figure out, is it dry enough to put managed fire on the ground during, say, winter months to get desired results? So this is just a time series kind of showing that study area there. But in addition to kind of building this on the OpenET modeling system, it allows us to have historical perspective. And so at dinner last night, we had some good discussion about, a lot of things about forest health. One thing that came up, though, was how crazy 2020 was. It was crazy in Monterey as well. 3 of the largest wildfires occurred simultaneously in the region. And so it's like the river fire, the Carmel fire, and the Dolan fire. The 2 top fires, they actually burned out in a month. They were really fast-growing, intense fires. The bottom fire, the Dolan fire, it took 4 months to burn. And so you can start to see some of the variations in fuel moisture and try to figure out how those might contribute to that pace of burn. And if we dive into the data for the river fire and kind of like look between 14 days before and 1 day before, you can really start to see how the landscape's beginning to dry out. And if we superimpose those thresholds, such as a 80% marker that I shared earlier, you can really see how data is kind of moving from this top plot, which is showing, moisture content on the x-axis. It's kind of moving towards that 80% and beyond. And so, while this is a fairly early on project, I think some of the key takeaways from me, I think ET is really providing a useful indicator of fire risk. And while, live fuel moisture content is maybe the variable now that makes traction with some of the wildland fire agencies, I think through more collaboration and ideas like Yun was sharing yesterday, where you kind of accumulate the anomaly in time, I think there's great opportunities to work with these agencies to more directly include ET data in their assessments. And this snapshot here is like where every time we drive in to take samples, like this is what the fire risk information is being distributed like. And so it's like I'm hopeful through this project and future relationship building that we can work towards more data-driven risk information. And so with that, I just want to say thank you and acknowledge the CSU ARI system, which really supported a lot of the student involvement here, in addition to the partners that have provided useful feedback along the way. So thank you.
Thank you very much, AJ, for this great talk. So any questions? Yes.
Really interesting and great work. What type of correction are you applying for aspect and shadow effects? Because we tried using OpenET in unirrigated areas, and you get crazy results where you can take a large area and it comes very close to what we know the actual ET probably is, but if you start going and looking at 30-meter pixels, you might see 4 centimeters of evaporation when you go across the ridge, and then some you see 40 centimeters of evaporation. So and that's due to temperature. That's due to temperature effects within water-limited slopes. And so, what are you doing to correct for that?
No, I think Yoon kind of addressed like how the models are dealing with that yesterday, and how Metric in particular I think does they have some good ideas on how to account for that aspect correction. For this work here, I will note, if you look at like the north and south face slopes in our study region, they're drastically different in terms of vegetation composition. And while we're not making any direct corrections here, I think by taking the modeling system and really looking at the change in time as more of that driver of the information for fuel moisture, it mitigates against that impact. But I absolutely agree there's always room to improve. And I think from the standpoint of getting at more accurate fuel moisture information, we're really trying to be more strategic about sampling across those different aspects as a way to understand, are we actually seeing a high bias for that? But in terms of like the ET data itself, I think Yoon addressed that quite well yesterday. But yeah, I'd be love to hear if you have any ideas on how we might want to consider it. But I think the change over time here is the thing that I think is important when you think about risk. And even some of the outreach with the local CAL FIRE unit, they acknowledge that samples on the ground for fuel moisture at some of those stations may not be perfect, but so long as they're imperfect in the same way over time and they can track change, that's still useful information to them. So
we can also follow up with you and to see the data abnormal that you see in your study, and we can discuss about your user case to see what we can help. Yep. Do you also have a question here?
I was just going to ask really quick if you could share, this is really interesting to see, you could share a little bit about the live fuel moisture content and how CAL FIRE uses that. My impression is that it's mostly absolute, right? Like that 100 or 80% threshold, thank you, that you were using. Is there some relative way that they use that to like prioritize, where they have boots on the ground or anything like that?
yeah, the governor's office recently started the Wildfire Information Technology Center, which is headquartered out of Sacramento and includes a CAL FIRE representative and a Department of Emergency Services person too. They're interested in this information for kind of strategic resource allocation at larger areas. Locally, it's more important for them to kind of like understand, really the risk state of, our area. And so I think it's more in terms of like the response to fires right now is how they're using it. One of the things here that, we've been talking to them about is, this is a first step towards providing, very granular information. And so if they're collecting data on the ground, they can kind of, bias adjust relative to what they're seeing themselves. The one opportunity I will mention is that, every time there's a prescribed fire or managed fire on the ground, they collect fuel moisture samples. And so while that's one point, this kind of allows them to kind of benchmark that to the area they may be covering with the managed fire project that they're working on. And so we're still kind of iterating on how this might be able to, feed into evaluating whether or not the prescribed fire that goes on the ground, whether it has the desired longer term effects that they're hoping for.
I see.
Yeah.
Could this also act as then a sort of prerequisite to help enable more prescribed fire to get on the ground?
Yeah, that's one of the things we're exploring right now is, whether or not there's periods of time outside of the fire season where the fuels are dry enough to get good impacts. It's like right now, in California, as green as can be. You can't, you know, you're not going to get useful. I don't know. They acknowledge it's just they're kind of crunched, and you know there's a lot of pressure to increase reductions in fuels across the state, and so trying to be creative about how they can achieve those goals. Yeah.
So it's mostly about increasing the window for prescribed fire and less about overcoming regulatory constraints, for example, about ensuring that you're within a certain window of.
It's trying to work within the system and identify windows of opportunity outside of the typical, the traditional periods of time that managed fire has been used. Yeah.
This is great, thank you. I had a question about how the relationship between fuel moisture and like the spatial orientation of the fuel plays out, and I totally see how this would be super useful for identifying the moisture condition of an area that you want to burn, because you would already have an understanding of kind of the spatial orientation of the fuel. But I can also see cases where ET is higher and fuel moisture is higher, but because of the like orientation of the fuel, it's actually potentially a riskier situation than maybe an area that's slightly drier but has a different fuel orientation. So can you talk about how you, if there's any thought about that within your work, or maybe areas of like future study, kind of thinking about, moisture content versus like spatial?
I apologize. I'm not quite following what you're asking directly, and so
I guess I'm wondering, like thinking about how moisture relates to like orientation of the fuel, like density of different shrubs and species, and how that relates to risk as well. So kind of.
Oh yeah, no.
Yeah.
No, thank you for bringing this up. I should have kind of shared, you know, this is just one piece of information as it relates to fire risk. The vegetation density and abundance is important as well. You know, I think one of the opportunities there is using some more of like that vegetation structure data, whether it's through the airborne LiDAR or things like JEDI from NASA. But, you know, another kind of area of interest that came out of attending the Fire Congress this past winter was the fire modeling community, and they're kind of interested in how these two variables, you know, interplay when it comes to, you know, how they might be coupled to better inform, you know, model projections. But yeah, if you have any ideas, I'd love to kind of pick your brain after the session on how to consider this. Yeah, Gabe.
I know there's been a ton of questions, so thanks for taking this. But what are you picking up when you're sampling? Like, what are you cutting everything down to the soil and like clearing a patch, or is it like just the detritus that's there among the living plants? You know, or are you cutting things down? You know.
No, it's I'd love to. Yeah, it's probably longer than we have time, but essentially, yeah.
Probably you can talk
I'll
about
ask
this.
you later.
Yeah, absolutely. Yeah. Yeah. Thank you.
Yeah, so it's really a nice discussion here. So if you have any, you know, further question, I do realize there are a few more questions there, but you can catch up with AJ after the session. And